Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video is created to review introductory transport phenomena based on the Welty, Rohrer, and Foster textbook. We are currently looking at the properties at a point section, and in this video, we want to review the fact that we asserted that pressure at a point is going to be the same in all directions. And as a reminder, pressure is the limit as the size shrinks to a small continuum point, delta A, of the change in the normal forces per unit area. So to prove that these are going to be the same in all directions, we can begin with a small prism of fluid shown here to the right. And the x-coordinate for this small elemental section is going to be delta x, or the little scripty dx. The height is going to be a little dy. The angle between them is angle theta. And then we have this slant surface here of length ds. And those heights, we can use all of our trigonometry relationships, right? So we know things like sine is the opposite over the hypotenuse. The slant is the hypotenuse in this case. And so for angle theta, the y element is the height, or is the opposite, excuse me. And the x component is our adjacent side, okay? So keep that in mind as we do this derivation. So the key thing here is that for a body at rest, we know that delta F, the sum of all the forces, has to equal 0. And that can be done kind of on a net basis, or we can look at these in a single direction. So if we look at specifically the x direction on this little prism here, then in the x direction, we have here this force here, and then we have the x component of this force, okay? So therefore, this one is delta Fx, right? It's the Fx going in the positive x direction. And this one is going in the opposite direction, but we only want the normal component. So delta Fx minus delta Fs times sine of theta, that's the normal component, or the slant force taken in the x direction. That sum is equal to 0. But we also know trigonometry. And trigonometry says that I can relate that to the size of these elements as sine of theta is delta y over delta s, right? So now I can substitute this delta y over delta s into my force balance to get delta f of x minus delta fs times delta y over delta s is equal to 0. And if you go through and multiply everything through by delta y, delta z, okay, so I've added in this z component, the depth, I get delta fx divided by delta y, delta z, minus delta fs over delta s, delta z. Now, go back and remember what are the definitions of the normal stress. The normal stress is the limit as delta A goes to this small continuum point of delta F normal over delta A. And so these are, in fact, our normal forces over these elemental areas. For the x1, the elemental area, it's acting on this space of delta y by delta z. And delta Fs is acting on this section of size delta s by delta z. Therefore, the normal stress in the x direction minus the normal stress on the slant direction is equal to 0, or sigma sub xx is equal to sigma sub ss. Okay, well, that's not the full story. That tells us something, right? But we need a little bit more. So what happens if we look in the y direction? So very similarly, we're going to use our the y component this time of our force on the slant side and our component that's acting in the upward direction down here. But we also now are going to have gravitational force. We need to take into account the weight of the fluid acting down because that is another force, right? Okay, so if we do that, we have delta F in the y direction minus the y component of delta Fs, so that's minus delta Fs times cosine of theta. And then we have the weight of the space of this little prism. And so that's the density of the fluid times the gravitational acceleration times the volume, which is 1/2 of delta x times delta y times delta z. This time we can say that cosine theta is delta x over delta s, which can be substituted into our force balance. Delta Fy minus delta Fs times delta x over delta s minus 1/2 rho g delta x delta y delta z. And that's all equal to 0. This time we're going to divide through by delta x delta z. That leaves us with delta Fy over delta x delta z minus delta Fs over delta s delta z because the delta x canceled, minus rho g delta y over 2. And that's going to all equal to 0. So now let's take this size down to our small point, okay, in the continuum. So if we do that, delta V goes to 0, or very close to 0, essentially 0. So the delta Fy over delta x delta z is sigma y. Delta Fs over delta s delta z is sigma ss. Rho g delta y over 2 is 0. Because in order for the size of the space to go to 0, we know that delta y needs to go to 0 also. And so therefore, we once again have demonstrated that the normal stress in these two directions, the y and the s direction, are equal to each other. But combine that with what we said just a moment ago, and so we know that that's also equal to sigma xx. Therefore, we have in fact demonstrated that the pressure is going to be the same in all directions at a point, and that the pressure is the average of all normal stresses on that element. So that concludes this video lesson. In the next lesson, we will begin looking at how properties vary from point to point in a space. Thank you very much for your time.